myself Surisetty Madhuri, bearing roll number 19BQ1A04E8, and today I am here to present a topic in optical communication, and my topic is signal distortion in optical fibers. Signal attenuation, also known as fiber loss or signal loss. Signal attenuation is one of the most important properties of an optical fiber because it largely determines the maximum unamplified or repeater less separation between a transmitter and a receiver. Since amplifiers and repeaters are expensive to fabricate, install and maintain, the degree of attenuation in a fiber has large influence on system cost. Of equal importance is signal distortion. The distortion mechanism in a fiber cause optical signal pulses to broaden as they travel along a long fiber. If these pulses travel sufficiently, they will eventually overlap with neighboring pulses, thereby creating errors in the receiver output. The signal distortion mechanism limits the information carrying capacity of fiber. And next is attenuation. Attenuation of a light signals as it propagates along a fiber is an important consideration in the design of an optical communication system, since it plays a major role in determining the maximum transmission distance between transmitter and a receiver, an inline amplifier. Because the attenuation mechanism is in a fiber or absorption, scattering and radiative losses of the optical energy. Absorption is related to the fiber material, where scattering is associated with the fiber material and it with structural imperfections in the optical waveguide. Attenuation moving to radiative effects originates from perturbations. Radiative effects originate from perturbations, both microscopic and macroscopic, of the fiber geometry. Attenuation events. As light travels along a fiber, its power decreases exponentially with distance. If P of 0 is the optical fiber in a fiber at the origin at z equal to 0, then the fiber P of z at the distance z further down the fiber is P of z equal to P of 0 e power minus alpha pz. And next is absorption. Absorption is caused by the different mechanisms. Glass material, intrinsic absorption by the basic constituent atoms of the fiber material. Absorption by atomic defects. Absorption defects are imperfections in the atomic structure of the fiber material. Examples of missing molecules, high density clusters of atom groups, or oxygen defects in the glass structure. These absorption losses are negligible compared with intrinsic and extrinsic losses. The absorption effects is most significant when fiber is exposed to ionizing radiation in nuclear reactor, medical therapies, space mission. The radiation damages the internal structure of fiber. The damages are proportional to the intensity of ionizing particles. This results in increasing attenuation due to atomic defects and absorbing optical energy. The total dose a material receives is expressed in the units of radar of SI. One radar of SI equal to 100x or 0.01 joule per kg. Higher the radiation, more the attenuation, as shown in the figure. If the intensity is higher, if the radiation intensity is higher, then the attenuation is more. Second one is extrinsic absorption. The extrinsic absorption is due to impurities present in fiber material such as transition metal impurities, OH ions. This absorption occurs due to electronic transitions between the energy levels and because of charge transition from ion to another. A major source of attenuation is from transition of metal impurities, ions such as iron, chromium, cobalt and copper. The losses can be up to 1 to 10 dBr kilometers. The effect of metallic impurities can be reduced by glass refining techniques. Another more intrinsic loss is caused by absorption due to OH ions. Impurities dissolve in glass. Vibrations occur at wavelength between 2.7 to 4.2 μm. The absorption peak occurs at 1400, 950 and 750 nanometers. And next is intrinsic absorption. It occurs when material is in absolutely pure state, no density variations and homogeneities. Thus, intrinsic absorption sets the fundamental law here on absorption for any practical material. Intrinsic absorption results from electronic absorption bands in UV region here on absorption for any practical material. Intrinsic absorption results from electronic absorption bands in UV region and from atomic vibration bands in the near infrared region. UV absorption decays exponentially with increasing wavelength. Infrared region is above 1.2 μm. The optical waveguide loss is determined by the presence of the OH ions and inherent IR absorption of the constituent materials. The inherent IR absorption is due to interaction between the vibrating band and the EM field of optical signal. This results in transfer of energy from the field to the band, thereby giving rise to absorption. This absorption is strong because of many bands in the fiber. Attenuation spectrum is for the intrinsic lock mechanism in pure GE, as shown in below figure.